Uh, my name is Goran Slavic. I'm a network development engineer at Omonia d.o.o. Belgrade. And we are going to talk about implementation of software router cluster. Um, a small agenda, what are we going to talk about? In the introduction, the software router as it is, for all of you who haven't been to before in the meetings. And evolution of ISP infrastructure, how does it go, in what point do you actually need some stronger routers that can accept the full BGP table, full global BGP table. Then we're going to talk about router cluster features, about how you monitored such a router cluster, about the core of that router cluster that's a control server, about some benefits, about some drawbacks, and after the theoretical part, we're going to go into what was actually implemented until now in the network of Omonia, and a couple of conclusions at the very end. In introduction, in this decade, we usually use the catchphrase cloud, and we push everything to the cloud. Actually, it's a small, sort of a joke. There is no cloud. It's always somebody else's computer. So cloud implementation is actually a buzzword of the whole decade. First we used cloud storage, then we used cloud processing, then we have some cloud services, then we had software as a cloud or something like that. And then we started to control things from the cloud, like cloud network controller, SDN control network that has a controller in the cloud. So a small question, is there a use case for some sort of centralized routing control within our network? Is there a use case for something that we can, very marketingly call cloud routing? Unfortunately, this is easier said than done, as we are going to see. First thing, the building block of this cloud routing cluster is a software router. Software router is not a new thing. There were several presentations at RIPE NCC conferences. Some of them were even done by me, some of them done by CEO of the Serbian Open Exchange. It's actually a server with routing software. It can be used as sort of a cheap, full global BGP table routing. Software that can be used is either Quagga or BIRD or OpenBFD or FFR routing. It has ability to process several full BGP tables. That is the biggest benefit of it. And because it's run on server with, dual Xenon processor, it can do that very, very fast. Also, it doesn't have a lot of capacity because of some Linux kernel problems. It can only process 3 million megapackets per second. Depending on the shape of the traffic, the composition of the traffic, that is between 20 and 30 gigabits per second. There is one big benefit, and that is that the processor of such a server doesn't do a lot if you set it up correctly. That means that you can run all kinds of diagnostics and all kinds of applications on that empty CPU for your diagnostics, for your control, for your active monitoring that we heard about yesterday. Also, this presents a problem because it does have a limited bandwidth, and it presents a problem that there are serious modifications needed to be done on a kernel with a lot of things that need to be changed. And by definition of all this, this is not a universal solution. So why do we use it? Well, ISP kind of always evolves. In the beginning, it's a simple ISP. You have one router to your transit provider. That's about it. Then for redundancy, you need to have two providers, but you're too small to buy some large chassis from Juniper or for Cisco. So you usually use some software router, some sort of Quagga, just to dump that, all that global, about 1.5 million or 700 if it's a full BGP table. Several of them could be 2.1 million routes, prefixes. If you're a larger ISP, you grow larger, then you need two of those routers as a primary, as a secondary. Then somebody comes to you, usually a boss, and says, oh, we need some remote location where we will need global BGP table, and then we're going to use some tunnel to go to the rest of the network. But it's only a temporary solution. Don't worry about it. Just set it up this time, and then later when we buy capacity to there, it's going to be okay. But there is a rather nasty saying, there's nothing permanent like a temporary solution. So in the end, your management likes this idea and says, okay, we're going to do it from now on. We're only going to do through tunnels and global peerings and all those things. And suddenly you end up in a situation where you need to control several of those routers all the way through a network. And you would like to have that centralized in order to know what you're doing. So what is the idea of a software cloud cluster? It's one control server that's also a router, but we're going to see why it is a router, that has BGP sessions to two, in this implementation we call them d.o.o and Perun, Slavic gods for all of you who don't know. And those two routers have a common VRP protocol between them in order to have, to distribute that as an XCOP address. So in a case of failure of one of the servers, VRP is going to provide redundancy for such a communication. And we have two switches. Each of them has a connection between themselves in order for redundancy. And we have remote routers that are establishing BGP sessions to them. The BGP sessions are done on the physical interfaces of these two servers. So VRP address is not used for BGP sessions. They're going to physical addresses of those routers, two routers, and VRP session is just used for traffic or for redundancy. Of course, on the server side, we have link aggregation and all the things that we need to provide successful redundancies such an occasion. And these two software routers, okay, I said here identical. It's not identical, it's logically identical, so that traffic would go to one or to other. There are three types of BGP sessions in such an environment. There are only informational sessions from remote routers that go to control server. We just insert the routes into the control server so that it has them in its tables in order, so you can compare, you can see where the traffic is going, what were the local preferences, and so on, so that you can control what is happening and have all the information of all the peering sessions of those routers. You have routing sessions. They're not good here. They actually provide prefixes to these two routers. And we have yellow sessions that are bilateral. So the routers inform the control server, and control server can push some sort of routes into the routing routers that are actually doing the routing. In this configuration, we set up that the first server, d.o.o, is actually used as a primary for IPv6 and is VRP redundancy for IPv4 in order to utilize both servers correctly, and so that we can actually have some sort of better understanding how much IPv4 and how much IPv6 we are having. Route cluster monitoring is mostly done, and control is mostly done on a control server, hence the name. And that server picks up on controls some sort of outside or inside data sources. That sources can be RIPE-DB, it can be peering-DB, it can be some geolocation service, RPKI communication, IPKI validator can be inserted on that control server. All the things that we want to control, all the things that we need to have at our fingertips in order to see what is actually done by a system. And of course, there are two SNP and SFlow collectors that are actually collecting the information from the network in order for us, with some API or with some sort of a control between control server and those collection SFlow and SNP collectors. It's actually an SNMP collector, but I'm using the actual one that we are using, PRTG, for such an occasion. And this kind of setup has the ability to verify prefixes with external databases. It can monitor traffic. It can analyze some sort of BGP changes. And we are not, using the actual routers for such analysis. We're using a different setup, the control server, to chunk out and to digest all the things that we are actually having in a network. And it has the ability to automatically generate configurations for the equipment that's under him. So command server is the key in this setup. It has prefix analysis and filtering. It can deliver up-to-date filters to software routers. So it actually, pulls some sort of changes and anything that we need and pushes those filters all to all the other equipment. It has ability to reroute traffic on remote routers, meaning if we see a failure, if we see that some sort of route is not working on some of the routers or it has some sort of a problem, we can actually centrally reroute or disconnect or stop BGP sessions, all kinds of things. It can analyze network traffic, but it's not a collector. You can actually collect on another location and use this only for control purposes. It can generate configurations, a whole configuration for both software routers, so not just parts or not just filters. It can control with SSH session, for example, other routers. And the interesting thing is because it is a software router in itself, the RTR control, it can reroute traffic to itself. It can insert a route and then say, okay, I'm the next hop for this. So you can analyze the traffic on the control server with some TCP dump or with Wireshark or with anything that you need in order to see that traffic. It's some sort of problematic traffic. It looks like a DDoS attack, but because it's a router, it would route that traffic back into the network. You're just you're inserting yourself as a man in the middle, so you will not lose any traffic by analysis. And of course, you don't have to go to the switch or something else to mirror the traffic. You can actually do it again from a single location. What are the benefits? It's the ability to control the whole cluster from a single location. It is ability to do a load balancing, not just between software routers, but generally load balancing. And because most of the configurations and ideas for configurations, who is peering with what prefixes are you announcing, even some sort of non-technical stuff can do changes. They can change, for example, shut down this session. And we are currently working on graphic user interface, but we want to establish functionality first. The control is actually done by a series of Python scripts that can be separately or in a sequence analyzed in order to generate the whole new configuration. But it doesn't have to be manually. It can be a cron process that will every minute, 10 minutes, hour, however close or apart you want to test what is done on validator RPKI, is there any update on RIPE-DB? Is there any change in the announcement or anything that you want? What is also important is IPv4, IPv6 synchronization, meaning you change something in IPv4 regarding certain AS that you're peering with, but you actually forget to do it on IPv6. To change a local preference or something like that. This kind of system does both configurations at the same time for IPv4 and IPv6. So your announcements over IPv4 or accepting prefixes over IPv4 are identical to what you are doing to IPv6. So there are no inconsistencies. Also, the configuration you saw has a rather high reliability. And the software routers are Linux servers. That means that any kind of program, any kind of code you can run on them, it's going to be done on dual Xen processor, and it's going to be very quickly realized. So all kinds of testing can be done. Unfortunately, there are drawbacks. There is, what I said a couple of times, inability to route more than 3 million packets per second, or about to the maximum of 30 gigabits per second of traffic. Setup is rather challenging because it requires a person that both has Linux skills and network skills. So it needs to be best of both worlds in order for all the things to be changed the way that should be. Unfortunately, like good things are propagated immediately, bad things are also propagated immediately, meaning that some sort of mistake is propagated instantly to hold the cluster. Also, software routers are controlled rather differently than regular routers, especially if we're talking BERT, who has a configuration that looks more like you are programming a router than you are configuring the router. It looks more like C code than configuration that you would see on Juniper or on Cisco. And because you can do all these things, management of your ISP can sometimes place an overwhelming burden on the whole system. Meaning they could say, oh, we want to route this over here, we want to route this over here, give this a local preference, give this a higher preference. So the system can sometimes be a little bit burdened by all those things that you can do, and you're actually going to try to do them, even though you probably shouldn't be playing that much with BGP. Now, all this is theory. This is an implemented solution, meaning what we actually did and what is actually in production in Omonia network. It's a semi-automatic solution. We are still not trusting our automatic system to do all the changes all by itself. So what we do, we let some of the Python scripts do their work, and then we manually check that, what was being done, what can be we correct, and so on. So we sort of go back. We do automatic filter generation, meaning that we automatically generate filters according to the RIPE-DB, and we automatically distribute those filters to software routers. We didn't install a separate S-flow collector because we were rather satisfied with what PRTG has as a sensor for S-flow. And we do most of our monitoring in PRTG, meaning triggers and all those things. So actually, this connection still doesn't exist. We are doing things about it, but we are probably going to leave that for the end, meaning the complete automation of the system will be left after we are sure that all components work in all weather and all extreme circumstances, DDoS attacks and something like that. Currently, it has a command-line interface, but like I said, we are working on a graphic user interface. What is nice, we have automatic black hole propagation, meaning that actually you just insert one line in the code of control server, and then it propagates the black hole routes to both routers. The routers announce with proper BGP communities to upstream providers that they should black hole that traffic, and we automatically go to our scrubbing service and announce that prefix only to them, so that traffic will flow only through the clearinghouse of our network. And all other routes, all other directions of ingress of some DDoS traffic are going to be shut down and black holed. Unfortunately, we found some rather big problems. Firewall or firewall D or IP tables on such a large traffic can cause problems. So we are we have been very, very surprised of how much we get CPU load on firewall subsystem when we use this configuration. Also, we encountered problems with MLAG, meaning that between instances or servers that are in MLAG, you actually have problem with IPv6 load balancing. It doesn't work like it should be. Hashing on IPv6 and hashing on IPv4 are kind of broken with the equipment that we used. So we needed to, sort of jerry-rig some sort of load balancing. Also, because it's a semi-automatic system, we now experiencing we are experiencing a slow response time, so more automation will need to be implemented in order for the system to work as it should. And we would need to establish some sort of better communication, or even some Ansible scripts or something like to non-software routers in order to control them even better, not only through BGP communities. And of course, the last but not the least, this whole setup was done on 1.6.4 bird. We need to migrate to 2.x in the near future. Conclusions. Control analysis mechanism actually works without any problems. That part we are very satisfied with. We are satisfied with the ability to generate route and prefix reports on analysis. We can run through on the control server through all the routes in all the tables and see what we like, what we don't like. We can monitor who is receiving what prefixes. We are also happy with the response time when we need to implement our anti-DDoS measures, meaning that actually that propagation of that black hole route is actually doing borderline instantly. As fast as you can detect it, it's already done and already redirected to scrubbing service. Also, redirection and analysis of traffic on the control server is actually doing just fine. Unfortunately, lack of bandwidth on software routers need to be addressed. There are some rather nice papers, even some implementations, but considering we needed this for production right away, we implemented this. As soon as we find something better, we are going to implement that. Also, lack of firewalling is a challenge because we cannot currently implement all of the manners directive into our ISP, but of course, as you see, it's a work in progress. And while these results look promising, there is a lot of work to be done. I don't know if this animation is working. Yes, actually, you can monitor a bunch of routers, and then like in some sort of matrix or sonar readouts, you can see when there is a large, for example, this is the droppage of 2 full BGP sessions. So you actually see this. If it's all black, then it's okay. And then there is disturbance in the force or disturbance into these 2 routers that drop the session. So you can plainly see that you have a problem. This was implemented this morning, so that is why it's a last slide. So this is our idea.